Hello, this is not quite going to be the video that I had in mind from last week. My computer is still chugging away trying to do the rendering for the second of the videos that I had in mind. In the meantime, I wanted to make this video to address what I felt were the misconceptions of a flat earther who I had a conversation with in the past week related to the last two videos that I made. And it all seems to stem from the videos being made by various flat earthers who seem to be struggling with perspective and just where these towers should be based on their distance. This video is really going to be more of a show and tell of the script that I wrote, how I went about telling Pavre to generate it, along with the math that was involved to generate all of the data points. So at the moment, this script is still quite messy. I haven't cleaned it up. At this point, I set up a bunch of variables that control where the camera is located, the direction it's pointing, how high the water level is, how far in or out the camera is zooming, etc. Then I have an external file that I can control through a script. So I have a script that will override these values for that frame. Then it calls Pavre to generate the image. Then it recalculates all of these values and then runs it again for a new data file. So this section allows me to control all of the various settings. Here I'm iterating through all of the data points in 3D space that represent each coordinate for each of the 3 points in the triangle. This allows me to define the topology that represents the terrain. So now I'd like to focus on how I went about calculating these data points. These are all represented in kilometers. So I created a spreadsheet and I'm going to make the spreadsheet available. So check in the description below for the link to this file. Here I've specified the constant for the Earth radius in meters. Refraction is standard 7/6. And the radius of the Earth, including refraction, would be the product of these two. Here you specify the geo-coordinate of the observer. This would have been where that photo was taken, and the observer height. This section allows you to calculate the distance between two geo-coordinates, and that uses the Haversine function. These are the intermediate calculations, and then this cell with the blue background is the output of the calculation. So here I'm using the image that I stitched together from one of Ruhif's videos that he made, because Ruhif has identified a bunch of peaks. So let's say I want to represent Bofell. All you would do is copy this line. So in this case, I just grabbed the geo-coordinates of Bofell from my application, along with the elevation data that was provided by NASA. In this section of the script, I have a ground height and I have a separate height. In the case of a tower like this, and you could add multiple towers as well, ground level would represent the ground level where the tower is sitting upon. In this case, using the elevation data from Google Earth, it said that it was 11 meters above mean sea level, and the tower's height was 158.1 meters high. In the case of a mountain, I'm using the mountain peak, so the ground level is going to be 0. Here we need to calculate the relative distance, and that's where the Haversine function comes in. So you generally would not have to touch lat 1, ln 1, because that would be where you are, but you want to change lat 2, ln 2. So here I'm going to use the 14th row instead of the 13th, and that ends up calculating the distance. So now I'm going to copy this without formatting. The normal azimuth means that if you are facing due north, you're at an azimuth of 0. In this case, the relative azimuth would equate to the center of the image. So let's say this is azimuth 0. But in this case here, I'm focused on the Blackpool Tower. So I've indicated that the Blackpool Tower has a relative azimuth of 0. In this case, I specified Dow Crag as having a relative azimuth of about 0.1 degrees. This is just an example to show how the rest of the calculations are done. It doesn't have to be an exact value in this case. And then I've got Old Man of Coniston over here with a relative azimuth of about 1.3. I would estimate this as being a relative azimuth of -1. At this point, I've entered all of the data. Now I need to calculate each point in 3D space. If the Earth is flat, it should be relatively simple. Let's say I'm standing in this cell and the top of the Blackpool Tower is this cell. I'm looking to calculate the angle up from my horizontal. And so on a flat Earth, it would be the arctangent of this over this. Tangent really is the ratio between this length and this length, and the arctan is the reverse of that, which gives you the angle from that ratio, and that's essentially what I'm doing to calculate the angle up or down from my horizontal on a flat Earth. And with that, I get an altitude of 0.476417 degrees. If the Earth is a globe, I assume I know the lengths of all three sides of the triangle. So here, if you think of a triangle calculator, the trick is to calculate all of these angles. If you are at A and you are looking at point C, the length between these two would be known, and the length would be 19 kilometers. The length from A to B would be the point between you and the center of the Earth, which would be the radius of the Earth plus your elevation above mean sea level. In this case, I'm not using the real Earth's radius, I'm using the effective Earth's radius, including refraction. So in this example, length A would be this. And then very similarly, the top of the Blackpool Tower to mean sea level plus the Earth's radius including refraction would be this. I have the three sides. Now calculate the angles in degrees. And looks like I just had to use the same units. I was trying to measure this one in kilometers and each of these in meters. Calculator.net also steps you through how this was calculated. In fact, that's where I got my calculations from. But given the three sides, it calculates the three angles. In this case, I'm interested in the angle from my location to the observation, which would be, in this case, the angle to C, 90.401 degrees. My altitude is that minus 90, which gives me an altitude of 0.400837 degrees. And so I've done the same calculations for all of the data points. Here you can see that on a globe Earth, you can see that Blackpool Tower is at an altitude that is higher than the altitudes of all of the mountains behind them. However, on a flat Earth, Blackpool Tower is at an altitude lower than the altitudes of all of the mountains. Finally, I have the altitude towards a point of interest such as Dow Crag or the top of the Blackpool Tower. I want to calculate where that will be in 3D space so I can generate all of these data points. And to do that, I use 3D trigonometry to calculate where the distance to the object in question is the radius of the circle. I have my horizontal angle, which is represented by the relative azimuth, and I have the vertical altitude that represents the angle up. The first thing I do is I use cosine of my altitude multiplied by the distance, and then I multiply that further by the sine of my relative azimuth. That will give me my x coordinate. And in this case, x would be the distance relative to my position left and right. To get the distance relative to my position forwards and backwards, it's the same as for x. The only difference is that I use cosine on my azimuth. And then finally, for the elevation up or down from my position, I'm using the sine of the altitude towards that point multiplied by the distance. Here I have the 3D coordinate space for the globe, and I do the same calculation for the flat Earth. The only difference is I'm using this altitude angle for the flat Earth as opposed to this angle altitude that I'm using for the globe Earth. Finally, the last thing that I'm doing is I am identifying every single elevation data point that I have available to me. I iterate through them all. I do the same kind of calculation, and then I generate this data file with each of these data points. So for anybody out there who's confused as to how you would go about calculating the relative height of one object to the other in 3D space, I hope this helps. If you made it this far, thank you very much for watching to the end. If you did like this video, I really would appreciate the thumbs up, the comment below, and the subscribe and all that other stuff. Thank you for watching, and I am going to see you in another video soon enough. So bye for now.